Okay, so we're at Arizona State University. This week is the Material Research Society meeting that's being held here at Phoenix. And Chen Chen here is giving a talk during one of the sessions tomorrow. We're here at ASU just practicing it and hopefully making a video we can put up on YouTube that'll summarize the talk he gave at MRS this year. So he'll be telling us about NMR tool, box for characterization of nanomaterials, and this is stuff that he's been doing as a PhD student here at ASU for the last several years. So Chen Chen, I'll let you take it away.
Sure. Hello everyone, my name is Chen Chen. I'm from School of Molecular Sciences at Arizona University. Right now I'm working as a research assistant in Magnetic Resonance Research Center, ASU. So when we talk about nanomaterials, until now the nanomaterials has been used in a lot of fields like drug delivery, and it can be used for imaging, and due to the special optical property of the nanomaterials, it can also be used for detection, catalysis, and also for the cancer therapy. However, when you try to extend more and more applications of nanomaterials, you have to make sure that the quality of the nanomaterial is good. So the real challenge here for the nanoscience today is the characterization of the nanomaterials. So first, when we go to the real stuff, first let's review a little bit about the NMR spectroscopy in the research, the ligand capping behavior at the surfaces.
So Chen Chen, what is the molecule you're showing here? And this is just the NMR of the molecule, not attached to the nanoparticle, right?
The molecule I show here is a very typical organic molecules people use in nanomaterial synthesis, especially the gold nanoparticle. It's an octodiol. So and all the NMR
so octothiol, and so it's common in gold because of the sulfur gold bonds that it makes a very strong bond to gold.
Yes,
directly.
Exactly.
And then the picture you show on the right is a picture of octothiol that's been bound to gold nanoparticles in kind of an arrangement that most people feel, and a surface coverage that people feel is pretty typical.
Yes.
And about what size is the gold nanoparticle there you're showing? Since there's not a dimension on that, is that?
It's about 1.5 to 2 nanometers.
So on the small side.
Yes.
But even then, it has quite a lot of surface coverage of stuff on it, and it's just that it's how these molecules bind on the surface here. How they bind right here on the surface. Do they bind to different faces differently? How heterogeneous and homogeneous do they find that we would like to find out in?
So first, let's look at the diol-capped gold nanoparticles. First, we did a couple common characterizations like UV spectroscopy, and also we did TEM to determine the size. So in the UV plot, we can see that there is no very significant absorption peaks there for this type of nanoparticles. It's because it's being proved that it has a semiconducting property, so it will show step-like absorption curve. And for the TEM, we know that the size of the nanomaterials we synthesize is about 2.5 nanometers. And also we tried the proton NMR to determine to get a first look at the NMR spectra of the nanomaterials, and we see that compared with the pure octodiol, the ligand on the surface actually show broad peaks. Here that the methyl group shows at about 0.9 ppm, and when you compare that with the methyl group in the pure octodiol, it's very broad. And also the same thing happened for the CH2 groups.
So you're basically saying comparing this peak right here.
Yes.
Number 8. Okay.
Right. And also you're going to lose the splitting patterns there. So for the reason of the broadening effect, so we show the illustration at the right side, because you have different facets because you have different facets for the gold nanoparticle surfaces, while the ligands capped to the different facets will show different chemical shifts And in general, you will have a distribution of chemical shifts there. So that's the main reason to make the chemical to make the resonance more broadened. And so here this slide just shows a very simple tools people can use to determine the surface coverage by using solution NMR techniques. So we chose DMSO as the reference to determine the surface coverage for the octodiol capped gold nanoparticles. We add a specific weight of DMSO in the solution, and also we weigh accurately the nanoparticles we put in the solution. After doing integration with the meso group and DMSO group in this final NMR spectrum, we can calculate the surface coverage of the octodiol molecules at the surface of the gold nanoparticles, and the result shows here is gold diol ratio is about 2.39, and we also it's here. And we also tried a classical method, which is TGA. It's a thermogravimetry analysis, and to determine the surface coverage, and it shows a very consistent result here. It's about 2.44. And then a very powerful aspect of NMR is that you can try some two-dimensional NMR and to get more information compared with the single-dimensional NMR spectroscopy. So here we use the proton-proton COSY and the proton-carbon HSQC, two very common 2D NMR spectroscopy to characterize the nanomaterials. So we can see that by using the diffusion coefficient, by using the diffusion order NMR spectroscopy, we can actually determine the size of nanomaterials with taking consideration of the ligand.
I have a question for you here then. So you did this for one size, and I assume this is still octal?
Octodiol.
This is still the C8 octyl thiol?
Yes.
So then if what you're saying is true, a good experiment to kind of prove that you're really measuring the distance between the size and the hydrodynamic radius is to, and this is all done in chloroform still, or
yes.
CdCl3?
Yes.
So you could take octal versus dodecal versus some of the bigger and bigger. In other words, you could make this carbon chain either smaller or make it larger, and you would expect, while this number would stay the same, that this would keep getting larger and larger. Has that been done yet? Have either you or anyone else you know of looked at diffusion weighting to really kind of show that kind of proof of concept that it really works in the way you would expect it to there?
I have done for the octodiol and carbon 12. So I have done two ligands, but I didn't show here. So we need more data.
Do you actually get an increase in size with the C12?
Yes.
You do?
Yes.
Is it significant? Is it, because I would expect it to be kind of pretty small. I guess the reason I'm saying that is because you draw these as being 100% extended change, but it's very easy to imagine that they actually, these are all methylene, so it's easy for them to kind of fold in, right?
Yes.
And since this is hydrophobic and it's going into a more polar solvent, you would think you would even have quite a lot of control here in that if you did this with, say, a C8 versus, say, make it a fairly big size, like double it to C16,
yes,
that you might not actually increase the hydrodynamic radius that much when it's in a polar solvent, because it'll sit there and come back down upon itself and more or less, really try to compact itself on the surface. But if you did it in a non-polar solvent like hexane or something like benzene, that it might really extend itself out more. Has anything like that been done yet, or is that still kind of in the early stages of looking at?
I don't think that has been done yet. So, and also we have another system to talk about, and it's amino acid capped silicon nanoparticles. I have two model systems in this field. The first one is the lysine capped silicon nanoparticles. Here I showed you guys just a cartoon, which is lysine at the surface of the silicon nanoparticles. So we applied proton to carbon and proton to nitrogen to study the system first. So from the proton to carbon CP mass spectrum here, we can see that the eta CH2 groups, which is the nearest to the side chain amine group, and its carbon chemical shift actually shift, and due to we think it is due to the protonation of the side chain amine group.
So you get kind of a large shift there.
Yes,
yeah.
The shift is very large, and we also demonstrate this by using proton to nitrogen CP mass. We can clearly see that compared with the bulk lysine, the lysine at the surface, for the lysine at the 6 nanoparticle surface, the backbone amine group still has the same chemical shift, but the side chain amine group has about 10 ppm chemical shift, which is contributed from the protonation state. And also we tried two-dimensional NMR. Here I showed you guys proton to carbon heteronuclear correlation spectrum. And by changing the mixing time here, the left one shows the 0.25 milliseconds correlation time, and the right one shows 2 milliseconds correlation time. By changing the correlation time, you can actually resolve the signal talking with longer distances here. So basically, if you apply a longer mixing time, you will see the correlation in a long spatial distance. So here we actually in 0.25 millisecond spectrum, we didn't see the talking between the CH2 group and the hydrogen bonding proton. But when we change to 2 milliseconds mixing time, we can successfully see this resonance here, which has a proton chemical shift of about 7 ppm. So also we tried DFT calculations to get the simulated proton chemical shift of this kind of hydrogen bonding proton, and the result shows that the calculated chemical shift for this proton is about 7.5 ppm, which is very consistent with the experimental data. And next we studied the alanine capped 6 nanoparticles, and the study here we conducted here is a little bit from the formal one, which is the lysine capped 6 nanoparticles. Also we determined the absorption profile for the alanine, and also we can see two-stage absorption, which the first one is the monolayer absorption, and the second one is the multi-layer absorption. And also we tried, in this study we prepared two different samples, which one is the low coverage sample, and the second one is a high coverage sample. And this work has been published in 2015.
Okay, so a couple of questions here, Chin Chin.
Yes.
Well, first, Tom.
Hey, good to see you.
You can say hi right there.
Hello. Are we presenting or are we recording?
We're recording right now.
Okay.
So Tom's visiting from Berkeley. He was used to be a student here and is here for the MRS meeting as well. So he's going to catch the second part of this talk.
Okay.
So this work you published, because this is mainly with Greg, right?
Yes.
Who's at SDSU, used to be here as well.
Right.
I don't think he's coming in town for the MRS meeting, but so it was recently published. And a couple questions I have on this. So one is unlike the past things, did you do any liquid state NMR of these? Because usually you kind of showed some of the liquid state first and then moved on to solid state. I mean, was any liquid state NMR done of these?
No.
Not at all?
No,
Okay.
we didn't try any liquid state.
And
So
then
these
you
are
say-
just hydrated, just like
That's
water
exactly
is
what I was going to get
hydrated,
next
yeah,
to.
yeah.
So
Hydrated is just,
hydrated means like what? I mean, dry means vacuum oven dried, or?
yeah, the hydrated sample here is that we only vacuum dry sample for a day, but for the dry sample, really dry sample, we actually pump the sample for half a month.
Oh, wow.
So basically, though, these are both white powders.
Yes.
Okay.
It's just one you haven't pumped for forever to get all the bound waters out of it,
Right.
and another one you really pumped the living fucking crap out of
Right.
until you could get every little bit of water
Yeah.
out of it. Okay, that actually helps a fair amount in understanding this. And then so in your het core experiments here again, so you were able, and these are all on natural abundant
No, this is
Okay, so these
we-
are labeled because
yeah,
the
we use
nitrogen
the
would have been
label.
really hard to do. So these are what's the labeling on the? You know, this is just you're buying amino acids, but you're buying labeled amino acids. So is this
Yes.
C13, N15?
C13, N15 double label.
So basically per C13, N15 labeled
Right.
amino acids that you're putting onto these. And then what is like? This is your silica nanoparticle. You're kind of cartooning here, and
Yes.
or here like what size of nanoparticles are you binding these to?
It's about the average size is about 7 nanometers.
Is this something? Are these silica nanoparticles that you're making with like an alkoxide method, like a TIOS or an alkoxide method, or this fume silica that you're buying, or what is the kind of silica you're using?
We just directly purchase this type of fumed silicon particles.
Okay, so it's not just really
Sorry.
discrete nanoparticles too. It's more of this typical fume state
That's right.
stuff, probably out of silicon tetrachloride or something.
Yes.
Okay. Any other while you're here?
No,
Before we move
yeah,
on?
I mean, I'm trying to get the context
Yeah.
from here.
Oh,
so
and
we're
now it's
at
over.
the end.
Boom.
Okay.
And now, yeah,
Context.
right at the end.
Done.
There we go.
Okay.
That's it.
Yeah. So a very no, and also we want to investigate the peptide and protein capped the nanomaterials, and we think that's a trend to make the nanomaterials more applicable in the future.
And then, Tom's in that one.
Oh,
You have
good.
you
I'm in
don't
that
have
picture.
quite really long hair. That's how often we update group photos.
That's old. That's old.
That's pretty old. Like
That's the best one
Yeah,
I can
you-
find.
yeah, that's-
that's the best one you can find.
Yeah. When's the last time? This is the most recent one that you guys have
You
done.
know, we're really
Yeah,
sad.
you guys are behind, yeah, yeah.
we're really.
Wow.
It's not
Yeah.
a good day. for
That's
us.
okay. That's okay.